Good morning to all of you. My name is Destiny Annabelle. We'll look at the parabola today, a fascinating geometric shape that can be found everywhere. It is far more useful in science and everyday technology than just a curve in math class, thanks to a unique optical feature. Let's begin now. First, some history. Conic sections are the curves created by cutting through a cone at different angles. The four main types are the circle, ellipse, parabola, and hyperbola. While each has unique characteristics, today we'll focus on the parabola. So what exactly is a parabola? Formally, it is defined as the set of all points that are equally spaced from a fixed point called the focus and a fixed line called the directrix. It appears to be a symmetric curve with the following key elements. The first one is the vertex, which may be at the top or bottom. Second, the axis of symmetry, the focus, and the line that passes through the vertex. Third, the focal point inside the curve. In addition, the directrix is a line that lies outside the curve. This configuration plays a major role in its optical behavior. So here are the general formulas of the parabola, which are regular and sideways. The only difference between both formula is the position of x and y variables, where the constants h and k are the coordinates of the vertex of the parabola. This is where the parabola becomes especially interesting. Among of all conic sections, the parabola has a distinctive optical property related to the reflection of light. The first part of this property states that any light ray traveling parallel to the axis of symmetry of the parabola will be reflected through a single point known as the focus. This means that even though the incoming rays strike different points on the curve after reflection, they all meet at the same point. This focusing effect is unique to the parabola. Conversely, if a light ray originates from the focus of the parabola, it will be reflected outward parallel to the axis of symmetry. This allows the parabola not only to collect light, but also to project it in a single direction. Because of this two-way behavior, parallel rays focusing at one point and focus rays becoming parallel. The parabola plays a crucial role in optical system. Think of it like this. If you shine a flashlight into a parabolic mirror, the light bounces out in a straight beam. If you point that same mirror at the sun, all the sunlight focuses into one hot pot. That's the power of the parabola. So why does the parabola have this special optical property? Why do all parallel rays reflect through a single point, and why do rays from that point reflect outward in parallel? The answer begins with a fundamental principle in optics known as the law of reflection. This law states that the angle of incidence is equal to the angle of reflection. In other words, when a light ray hits a reflective surface, it always bounces off at the same angle at which it arrives measured relative to the normal to the surface. This law applies to all reflective surfaces. However, what makes the parabola special is how surface its is how its surface is shaped. When a set of parallel light rays approaches a parabolic mirror, each ray strikes the curve at a different point. Even though these rays hit different locations, the slope of the parabola at each point is precisely such that the law of reflection directs every reflected ray toward the same point known as the focus. This is not a coincidence. The parabola is defined mathematically so that its geometry naturally satisfies this condition. As a result, every incoming ray that is parallel to the axis of symmetry is reflected at exactly the right angle to pass through the focus. Another way to think about this is that parabola knows how to redirect light. Its curvature changes gradually and smoothly, ensuring that the reflection angles are adjusted perfectly across the entire surface. Now, if we reverse this process, we observe the second part of the optical property. When a light ray starts at the focus and strikes the parabolic surface, the law of reflection again applies. Because of the symmetry and geometry of the parabola, these reflected rays emerge parallel to the axis of symmetry. This reverse behavior is just as important as the first. It shows that the parabola does not only collect light efficiently, but it can also send energy outward in a highly controlled and uniform direction. Because of this two-way reflection behavior, focusing parallel rays to a point and transforming rays from a point into parallel beams, the parabola becomes an extremely powerful tool, and this is why parabolic shapes are used to concentrate energy not only in the form of light, but also sound waves and radio waves. In solar concentrators, sunlight is focused to produce intense heat. In satellite dishes, weak radio signals from space are collected and focused onto a receiver. In car headlights and flashlights, light from a small bulb is reflected outward in parallel beams to illuminate a wide area efficiently. In summary, the optical property of the parabola is a direct result of two key ideas: the law of reflection and the unique mathematical geometry of the parabola. Together, they explain why this curve plays such a crucial role in optics engineering and modern technology. This is not just a theory, it permeates every aspect of our existence. Here are four compelling instances. Number one, Hubble Space Telescopes and other reflecting telescopes. Clear, deep space images are produced when parallel light from far off stars reflect off a parabolic mirror to a single focus. Car headlights. The focus is where the bulb is located. The road ahead is illuminated by a powerful parallel beam of a light that bounces off the parabolic surface. Third, satellite dishes. Even from thousands of miles away, incoming TV or radio signals bounce off the dish and converge at the receiver at the focus. Lastly, solar concentrators. Parabolic mirrors are used in solar power plants to concentrate sunlight onto a small area, producing electricity and high heat. These are all based on the same optical principle. To summarize, the parabola is a conic segment that has a directrix and a focus. Parallel rays can be focused to a point by its shape and vice versa. Telescopes, flashlights, satellite dishes, and solar energy systems all make advantage of this feature. In short, the parabola is much more than a math curve. It's a shape that helps us see farther, drive safer, stay connected, and harness clean energy. Thank you for listening.